Quantum Secrets Unveiled: How Unitary Operators Dance Between Mathematical Precision and Quantum Mystique, Preserving Inner Products, Constraining Eigenvalues, and Ensuring Orthogonal Quantum States. In our problem today, A.30, a unitary transformation is one for which 𝐸 equals I. So part A, show that the unitary transformations preserve inner products in the sense that U acting on alpha, U acting on beta equals alpha beta in the inner product for all vectors alpha beta. In B, we're tasked with show that the eigenvalues of a unitary transformation have modulus 1, which we've kind of talked about in the previous sense dealing with their determinants. And then C, show that the eigenvectors of a unitary transformation belonging to distinct eigenvalues are orthogonal. And so, the reason why we need these in quantum mechanics is that unitary transforms are crucial in quantum mechanics for several fundamental reasons. A, or part 1 of this, is preservation of probability, which corresponds to part A of this question. If the inner products are preserved, that means that we can apply these without having to renormalize and things of that nature. And here's a great concept from the block sphere from a research paper, where if we apply a unitary transformation on the position vector, we still remain on the block. So we preserve our inner products and therefore our probabilities. The second is conservation of quantum information, which runs along the same lines because we don't scale anything with these. And this becomes the concept of the eigenvector or eigenvalues have a modulus 1 value. So because we have a modulus 1 value, we don't do anything but add an arbitrary phase factor, which we've seen time and time again throughout the book. It's taken out as we normalize. So everything for information is still there because we're not scaling in the sense of eigenvalues being greater or less than 1. And of course, our next point would be the orthogonality of quantum states. Because these distinct values lead to different quantum states, for every distinct eigenvalue, we're good to go and have orthogonal quantum states, which is exactly what we need. A couple more points on this topic would be the time evolution. Because to get the time evolution of these states, we have to apply the unitary transform. And as such, it would be helpful to maintain that everything stays the way we like it per each time frame that we're looking at. And of course, this leads us straight to quantum measurements, which is thankfully a unitary transform, so we have all these properties coming together at once. So part A and B go by pretty quick. The preservation of inner products is quickly shown by noting here that U' equals the U inverse for unitary matrices, which are represented by unitary operators, or vice versa rather. And so if we start with the concept of U acting on the alpha vector, U acting on the beta vector, color-coded accordingly, we know that we can put this from the ket vector onto the broad side via the dagger. Now, since the dagger is here, we can use the definition of unitary, and we know that U' equals the identity matrix, but with the identity acting on the broad vector, which is alpha here, we know that we get back to alpha, and thus we preserve the inner product. As far as modulus 1 eigenvalues, we have to first suppose that this leads to an eigenvalue equation. So that being said, the unitary transform acting on the ket vector alpha leads to some scalar lambda, which is the eigenvalue, of the same vector. If this is true, then we know that U alpha here in the inner product, we can break this broad, turn it into a ket by using the dagger notation. And then we see that, okay, I have U acting on alpha, U acting on alpha. That gives me lambda alpha. But thanks to the fact that that dagger is acting on that first curly bracket, we know that we get a constant here with the conjugate, and then that this lambda on the second alpha can be brought out just fine because it's a constant. Now the dagger only applies to this ket vector, which we can turn back into a brawl from the dagger, and thus we get the inner product here. with lambda squared because of lambda conjugate lambda. As such, we also know from part A that UA is equal to AA through the same method of using the Hermitian conjugate and putting it over to the bra side of the bracket notation. That being said, the identity comes back and we preserve the inner product. But since these are the same statement, we can equate their two results independently. And when we do so, cancel, we see lambda squared equals now 1 after the cancellation, assuming that the inner product does not equal 0, which we need to assume because we're going to normalize. And if this doesn't normalize, then we're not a good quantum state, so that assumption is good to go and we can get rid of it in the context of quantum mechanics. So we don't need to worry about dividing by 0 as the point of that. Nonetheless, magnitude here, we could take the square root. Now we said we get modulus lambda equals square root of 1, which equals modulus equals 1. So we're good to go. Part A and B were pretty quick. Part C, slight bit more work, but still not that long. So the uniqueness of the eigenvector is very important for us, clearly. So just like in part B, where we had to suppose that U satisfied an eigenvalue equation, now we're going to do that for both U on alpha and U on beta with different eigenvalues, lambda and mu respectively. If this is the case, we're going to focus on the beta term since that goes on the outside. And we see that if we take this term here and multiply it by the inverse on both sides, we get U inverse U acting on beta, U inverse acting on mu beta. So we're just taking this and multiplying both left sides by U inverse. What we witness here is that U inverse U gives us the identity, so we're good there. But this inverse can now act on beta vector directly. But because we're unitary operators, we can go ahead and change that inverse to a dagger, and now the fun begins. This tells us that beta, from clearing this side up, goes here. Go ahead and draw a line there. Goes here. This result goes here. From that point of view, we can now go ahead and manipulate this and shove this mu over here. And that leaves us with U dagger beta here. And then from here, we can rearrange leading with this term now, which we'll see why that becomes important in just a second. And we see that 1 over mu multiplying onto the beta vector is equal to mu star acting on the beta vector. And acting just means multiplying in this case since it's a scalar. This is because we just showed in part B that the modulus has to be 1, right? So if U conjugate U equals 1, then we know that U conjugate equals U over, or 1 over mu. I don't know why I keep saying U. Mu conjugate equals 1 over mu, so we're good there. And that's why we can satisfy this. All this now comes together when we consider beta in the inner product with U acting on alpha. And then we see we have the beta dagger, put that into the ket with the dagger, easy enough. Therefore, U acts on alpha, the vector. And again, we'll leave that there. Alpha now gets the eigenvalue treatment. So we have lambda alpha. Lambda comes out front. We're good to go. Now, the result we previously just made can be put together here. Because if I have beta and U acting on alpha, I can put this U onto the other side with the dagger. And I know that I can deconstruct the inner product by U dagger beta in the ket now if I put a dagger on the outside. And that, again, transpose conjugate, make sure all our dimensionalities match. And we know that U dagger beta equals mu conjugate with the beta vector in the dagger notation. So from there, take the mu out of the dagger. 2 conjugates puts us right back to the actual value or the original value. Then the dagger on the ket turns that into a bra and we get back the inner product. Now, once again, we have 2 equations here thanks to the same definition, beta, U, alpha, and the inner product. And now we can go ahead and manipulate these and we'll take their difference to do so. Since we have this going right there, this going right there, we see that taking their difference, we get a 0 on the left-hand side, but then we have lambda and mu respectively, lambda minus mu. All the work we did in the first part of this section of C was to be able to put this mu as a non-conjugate term out front. So a bunch of algebraic manipulation, but it comes out very nice now because we have lambda inner product minus mu inner product, and they're the same inner product, so we could factor them out. Now, what this tells us is that since we have 0 on the left-hand side and an inner product on the right-hand side, if lambda does not equal mu, then the inner product of the two vectors vanishes and we get 0 equals the inner product. As such, that means that we're orthogonal. Okay, so if we are distinct eigenvalues, the eigenvectors must be orthogonal. If this is the same eigenvalue, since we're assuming distinct, that tells us that we're the same vector, and we see that the difference here would be 0, so we're good to go. Either way we go, we got it covered, and these transforms are very important to quantum mechanics as a whole, and there will be several links for articles on it because a quick 10-minute video does not do this justice. That being said, we got one more question in this appendix to go, and then it's off to a new book. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel, and it's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.